Hello and welcome to my YouTube channel. In this video, we are going to talk about analog to digital conversion using STM32F44 6RE microcontroller. This is the part 1 of the series. In the next video, we will see how to implement different tasks using A to D in the STM32F44 6RE microcontroller. So let's start the video. First of all, let us try to understand the definition of ADC and DAC. ADC stands for analog to digital converter and DAC stands for digital to analog converter. So basically, analog signals are time varying signal which changes its magnitude and frequency as well as phase with every smallest possible time. These signals can be generated by nature, for example heat, sound, light, temperature. All these signals basically are analog signals. These analog signals are fed to the analog to digital converter ICs which are present inside the microcontroller. Then these signals are processed by the ADC of the microcontroller or microprocessor. Then the analog signal is converted to digital signal, which is nothing but a combination of zeros and ones, and they are stored in the memory generally. And whenever we need to regenerate the analog signal, we pass these digital signal to DAC, which is digital to analog converter, and then we can play those signals using any appropriate device. For example, here we have considered mic or microphone as the input signal which is providing the analog signal, and speakers are representing the output signal, or they are generating the output signal. Now let us have the definition of A to D or analog to digital converter. By definition, A to D or ADC is an electronic device that converts analog signal, which is continuous voltage or current signal, into its equivalent digital signal, which is discrete values that can be processed by digital systems. Whenever we say digital systems, we are talking about systems which are designed using microprocessor or microcontrollers. And what is the purpose of converting these analog signal to digital signal? The purpose is to enable digital systems like computers and microcontrollers to process analog signals such as sound, light, temperature, maybe heat, or any other signal which is generated by the nature. Let us talk about the key concepts behind A to D or analog to digital conversion. First of all, what is analog signal? Analog signal is nothing but a continuous signal that represents physical measurements. Physical measurements means entities which are present in the nature. For example, voltage or current in our case. A digital signal is a discrete signal represented by binary numbers or series of binary numbers which are represented in zeros and ones. Why the ADCs are important? ADCs or analog to digital converters are important because they allow analog input from sensors. For example, in our case, we showed that microphone was used as an input signal. So microphone was providing the input signal and therefore microphone was acting as a sensor. Similarly, we can have different sensors like temperature sensor, light sensor, and so on. So the input analog signals from these sensors and other sources are then converted into digital signals and stored inside the digital devices. And this allows us to process the data or process the analog signal and store them and analyze them in digital format. So using those data, we can design good filters, even sound synthesizer or any other application, because we cannot directly process those signals that efficiently compared to digital signals. Let us talk about the working of ADCs. So ADCs first sample the signal or sample the analog signal. So that process is called sampling. So every analog signal is first sampled, and that process is nothing but measuring the amplitude of analog signal at regular interval. So we have two parts of a signal. For example, if we have an analog signal, okay, then we have time and amplitude. So what we are doing here is we are sampling the amplitude as well as time and taking different samples of these signals at different time. For example, if I show the samples in blue, then we'll be taking different samples of the signal at different time, and these samples will be then used for further processing. So this is the first step which is taken by the ADC, sampling. And sampling rate is one of the very important factor. So according to Nyquist theorem, sampling must be taken at least twice the highest frequency component. So whichever analog signal you are going to process, take the highest frequency of that analog signal, and from that signal at least we must be taking two samples from the highest possible frequency. This is what Nyquist theorem said, or we can say Nyquist theorem said that there must be at least twice the highest frequency component of a signal to accurately represent or regenerate the analog signal. Then comes quantization. So sampling basically is taking the samples in time domain. So sampling, whenever we say sampling, we are more focused on the time part. Okay. So sampling is done in time domain. And then comes quantization, and whenever we say quantization, then we are more focused in the Y domain. Okay, so quantization. What is quantization? Quantization is the process of mapping sampled analog values to discrete digital levels. So here in the Y-axis, we will be representing these levels in digital values. Okay, and these values are called the quantized levels of the analog signal. For example, quantization is directly related to resolution, which is one of the most important parameter of any ADC. Resolution is nothing but the number of discrete levels into which the analog signal is divided, generally expressed in bits. For example, if we have an 8-bit ADC, then we will have 256 levels, that is 2 to the power 8. Okay, 256 levels, and we will be dividing that analog signal in 256 levels. Let us look it into like this. So we have the analog signal, we have the Y-axis amplitude, time in the X-axis. So during quantization, if we have 8-bit ADC, then we will have 256 levels. Okay, these are the 256 levels in which the analog signal will be divided or sampled. Similarly, for a 16-bit ADC, we can have 65,536 different levels. So the higher the number of bits, the better the resolution. Now after quantization, ADC encodes the signal. And what is encoding? It is nothing but the process of converting quantized values into its equivalent binary form. So depending on the number of bits, we can have different number of levels, and these levels will be encoded into binary form, and that binary form will represent different voltage levels. So the binary output or the final digital representation of analog signal, which is used for further processing or storage in digital system. These are the binary inputs which are generated by the ADC for storage in the memory. Now let us look into some of the calculations, basic calculations related to ADC. First and the foremost important parameter is the ADC's resolution. So resolution is number of bits used in the ADC, and it determines the number of discrete levels into which the analog signal can be divided. The formula used to generate the resolution is nothing but the number of levels, which is nothing but 2 to the power resolution. Like we discussed in the previous slide, for example, if we have 12-bit ADC, then we can have 2 to the power 12, that is 4096 or 4K different levels in which the analog signal can be divided, and that will represent the resolution. Now comes the quantization step size. So what is the quantization step size definition? It is the smallest change in the input voltage level that results in a change in the digital output voltage, or we can say the smallest level in which digital number can be or digital voltage can be represented. For that we can use this equation. Step size is nothing but the full scale voltage range divided by number of levels. For example, if we have 12-bit ADC and the full voltage range is between 0 to 5 volt, then the step size will be 5 volt divided by 4096, which will come approximately equal to 1.22 millivolt. And this is the smallest entity or the value which we can measure using a 12-bit ADC. So 12-bit ADC will have 0000000 and 0000. This is the 0 representation, and the next level will be 0000000001, and this binary value is representing 1.22 millivolt if we have the full range between 0 to 5 volt. So this is quantization step size. Next, digital output voltage. So digital output voltage is equal to input voltage minus reference voltage, generally the low reference voltage, divided by step size. For example, for an input voltage 2.5 volt with a full voltage range of 0 to 5 volt, the range in 12-bit ADC can be given by, or digital output can be given by 2.5 volt minus 0, which is the lowest voltage here, 0 volt, okay, divided by 1.22 millivolt, that is the step size of the 12-bit ADC, and it will come approximately equal to 2048. This is the count which the ADC will generate, provided if we feed the ADC with 2.5 volt. Then comes the accuracy level of any ADC, or we can say the error which ADC can generate. So the maximum error that an ADC can generate is nothing but is equal to plus minus 1 by 2 of the step size. So whatever is the step size, if we take the half of that, then the maximum error can swing either into positive half or negative half of the step size. Let us take an example. For example, if we have a step size of 1.22 millivolt, then the maximum error that ADC can generate is between plus minus 0.61 millivolt. Now, ADC in STM32F44 6RE microcontroller. So what are the features which are present in the ADC inside STM32F44 6RE microcontroller? Generally, STM32F44 6RE microcontroller has got 12-bit ADC. It uses successive approximation technique to convert analog signal to its equivalent digital signal. It has up to 19 multiplexed channels. That means we can have 19 channels to convert analog signal to digital signals, allowing it to measure from 16 external sources. So we can directly connect 16 sensors, 2 internal sources, and 1 VBAT, that is the line which will measure the voltage of the battery which is connected to the microcontroller. The A to D conversion or ADC conversion of the channels can be performed in single mode, continuous mode, scan mode, or discontinuous mode. The result of ADC is stored in left or right aligned 16-bit data register. So the results are stored in 16-bit data register, and depending on the user's configuration, it can be either stored in a left aligned or right aligned manner. The ADC in STM32F44 6RE microcontroller requires 2.4 volt to 3.6 volt. For full speed, and it can be provided with 1.8 volt for slower speed. Slower speed means slower conversion rate, and full speed means the maximum rate at which the conversion can take place. It supports 2 modes of conversion, namely single conversion mode and continuous conversion mode. There are other features which are not considered here or which are not discussed here. For that, I will recommend you to go through the data sheet of the microcontroller. With this, I would like to end the presentation. If you have any suggestions or comments, do share your suggestions and comments in the comment section. If you have not subscribed the channel, then I would request you to please subscribe the channel and press the bell icon so that whenever I upload a new video, you will get the notification. Thank you and have a nice day.